Hello, my name is Mark Snyder. I'm manager of the Process Applications Group at Bio-Rad Laboratories, and today I'm going to talk to you about ceramic hydroxyapatite, or CHT, and its uses for commercial protein purification. I'll start out speaking about the history of Bio-Rad and then move toward what CHT is and how it works, followed by a section on CHT applications. Then I'll discuss CHT platforms and finally key points for CHT. Bio-Rad Laboratories has had over 50 years of purification experience in the biomolecule field. We offer several types of purification media, including affinity, mixed mode, and ion exchange. We support all scales from pilot to commercial. Now a brief introduction to ceramic hydroxyapatite itself. Ceramic hydroxyapatite, CHT, is one of the leading media for biomolecule purification. It's a spherical ceramic form of crystalline hydroxyapatite, and this form allows it to be used in production scale columns at high flow rates while maintaining its unique separation properties. Now let's discuss how CHT works. On the surface of CHT there are two sites, calcium or C sites and phosphate or P sites. The P sites work via classical cation exchange with the amino groups on the surface of proteins. These interactions are dissociated with either neutral salts like sodium chloride or by increasing buffering salts like phosphate. They weaken or dissociate with increasing pH. The C sites, by contrast, work via classical metal chelation chromatography. They are much stronger than ionic interactions and will not dissociate with sodium chloride, requiring instead phosphate for the dissociation. Finally, highly phosphorylated compounds such as DNA, endotoxin, or retroviruses interact very strongly with the calcium sites. Sodium chloride causes stronger binding of these molecules to the surface by decreasing the charge-charge repulsion between phosphates. Next, applications using CHT. CHT is used for purification of a wide variety of biomolecules, including monoclonal antibodies, viruses, IgMs, and non-antibody proteins. In this table, I've shown the various impurities that are present in a typical process feed stream for monoclonal antibody purification. Now on the right-hand side, you see observed clearance in logs of these various impurities. Here you see that CHT removes a significant amount of all impurities present in the process stream. I want to specifically focus on aggregate removal, which is 1 to 2 logs, and in some cases removes aggregates down to the level of detection, in this case 0.03%. How do antibodies specifically interact with CHT? Most monoclonals bind weakly to the CHT calcium sites and much more strongly to the phosphate sites. Phosphate buffer itself will simultaneously, as I've indicated, reduce both types of bonds. We cannot individually control them. By contrast, setting a low constant level of phosphate suspends the weak calcium affinity interaction but leaves the ionic interactions on the P sites intact. The sodium chloride gradient or step then dissociates the ionic bonds eluting monomeric IgG. Aggregates, because of their multi-site attachment, eluted higher concentrations of sodium chloride. Impurities, such as protein A IgG complexes, or phosphorylated compounds such as DNA, endotoxin, or lipid-enveloped viruses, interact very strongly, as I've indicated, with the calcium sites, and desorb only in concentrated phosphate solutions. Finally, the mixed-mode interactions present on CHT offer unique opportunities for residual host cell protein removal. As a platform step then, sodium chloride elution from CHT at fixed low phosphate concentrations provides excellent reduction of the impurities I've already discussed. We have observed significant impurity removal with every monoclonal antibody evaluated to date, including murine, chimeric, and human IgG monoclonals from a variety of subclasses. The consistency of elution behavior with sodium chloride suggests that this step may be universal. Here is a typical chromatogram of monomeric IgG separation from its aggregate, as well as other impurities such as protein A, DNA, and lipopolysaccharides or endotoxin, on CHT using a sodium chloride gradient in low phosphate. This shows 2 HPLC-SEC chromatograms of an antibody preparation before and after CHT chromatography. Before chromatography, there was approximately 2% aggregate plus dimers. After chromatography, these levels were reduced to below the level of detection. Again, in this case, less than 0.03% of the total protein. Here you see aggregate removal from two different single-chain variable region antibodies, or SCFVs. The left-hand panel shows that active monomer can be separated from aggregate. The right-hand panel shows that not only can active monomer be separated from aggregate, but also from inactive monomer as well. As I've indicated, CHT can be used for a lot more than just monoclonal antibody purification. This slide shows a classical example from the literature, that of the separation of 5 different isozymes of lactate dehydrogenase from each other. Here you see baseline separation in a phosphate gradient. CHT can be used for the purification of IgM. Here I've shown a 3-step workflow comprising Unisphere S, our cation exchange Unisphere resin in bind-dilute mode, followed by Unisphere Q, our anion exchange resin in flow-through mode, followed by CHT in bind-dilute mode. And on the right-hand side, I've shown an SDS page gel with the purification of IgM through these various steps. Now let's discuss CHT platforms. Again, as I've already indicated, CHT reduces a broad spectrum of impurities in process streams and is a perfect complement to protein A in a variety of different platforms. One configuration that I'm not going to talk about is protein A cation exchange, CHT. The ability of CHT to remove contaminants supports its replacement of anion exchange chromatography in a 3-step workflow. CHT also can be used before or after HIC chromatography in another set of 3-step workflows. This table shows the impurity removal of a protein A CHT 2-step workflow with an IgG1. You see that all contaminants were reduced to below the level of detection. Here we see the 3-step purification workflow for IgG comprising protein A followed by Unisphere Q in flow-through mode, followed by CHT in bind-dilute mode. This table shows the starting level of impurities followed by the level of impurities after CHT, and again you see that the impurities are reduced to below the level of detection following CHT chromatography. Now a few key points about CHT to take home with you. First, CHT is a robust material and it's in many licensed products worldwide, as well as in numerous products in all stages of development. CHT is easy to work with and very robust, provided that simple guidelines are followed, and it's extremely easy to pack. See your Bio-Rad representative or the CHT application guide for more information. We'll be happy to help you address any questions you might have regarding CHT. Again, my name is Mark Snyder from Bio-Rad Laboratories. Thank you very much. Please visit biorad.com/ad/CHT for additional information and to receive a free sample of CHT media.